Hello students. So in the previous class we concluded up the Sturm-Liouville problem, and today we are going to start Laplace transform. You may have also heard about it, integral transform or Laplace transform, and some of you must have also done it. So basically in the next 3 lectures we will talk about Laplace transform and how we can use it to solve ordinary differential equation. So before we start Laplace transform, you also know what is an improper integral and what do we mean by functions of exponential order and all. Of course, here we will define all of them. So let us start with Laplace transform, its formal definition. So the Laplace transform of a function capital Ft is a scalar function which will be denoted by the symbol small f s or L of Ft, or some people also write it f cap s. Either one of them is valid, or you can also write L f t. So different books have different notations. So is defined by f of s, which is L of f of t, as integral from 0 to infinity e to the power minus of st f of t dt, where s is greater than 0. So s is called as so basically let us call this equation number 1, where s is called the transform parameter. So as you can see, ft can be any function of small t. So it can be a constant, or it can be sin t, cos t, log t, to the power t, some polynomial, or a function mixture of exponential, sine and cos and all that. Later on we'll see that it doesn't always have to be smooth functions or nicely behaving or our classical functions. It can be any function, but it needs to have some kind of criteria, whether it is bounded or piecewise continuous. That thing we will state as a theorem. Now the inverse of the inverse Laplace transform, sometimes it is called as inverse Laplace transform. Inverse Laplace transform will be defined by L inverse of f of s. We can have second bracket f of s, which is equals to f of t, if f of s is the Laplace transform of capital Ft. Laplace transform, that means you can only go back to the previous function if f of s is the Laplace transform. So unless you know the Laplace transform, this Laplace transform of which function you have, you can't be able to go back to that function, right? So you need to know that fs is actually the Laplace transform of some function. That we will come how to calculate, but that you should know. Laplace transform of Ft. And L inverse is basically called as inverse Laplace transformation operator. So this is called as inverse Laplace transformation operator or Laplace transform operator. Okay. So this Ft can be any arbitrary function. So let us calculate Laplace transform of some classical functions that we already know. So suppose our Ft is a constant function c. So it's a constant. So then what will happen? We'll have L of c is equals to integral from 0 to infinity c into e to the power minus of st dt, because our Ft is c. So this will become c e to the power minus of st by minus of s integral from 0 to t, 0 to infinity. Ideally you have to take limit b tends to infinity 0 to b, because this is an improper integral. and since the improperness is not with respect to the function, that means at t equals to 0 this function is 0, at t equals to infinity this is tending towards at t equals to 0 the function is 1, sorry, the function is 1, and this function e, and therefore c into e to the power minus of st will become c, and at t equals to infinity this will simply become 0, so c into 0 will be 0. So the function is not creating any problem at the endpoint, so therefore you have to do limit b tends to infinity 0 to b. But since we are familiar with the improper integral, I wrote it down directly. So now what will happen is at t equals to infinity this is going to 0, and at t is equals to 0 this will be minus minus. So this is c by s where s is positive. So that means Laplace transform of any arbitrary constant will be c by s. So from here we can write Laplace transform of 1 is 1 by s where s is positive. Right. Now if I have let us say a second example is Laplace our ft is t square, or let us say t to the power n. So then Laplace transform of t to the power n will be integral from 0 to infinity e to the power minus of st t to the power n dt, right. So from here if we want to calculate, so first of all Laplace transform of t square, we can calculate Laplace transform of t. So if we calculate Laplace transform of t, it will become integral from 0 to infinity e to the power minus of st into t, will come back to here dt. So this will become first function, second function we can do, and from here it will become this I am keeping it as first function, so e to the power minus of st by minus of s. I mean I do not want to do this, it is too basic, but let us do it anyways. Then derivative of the first function, so that is 1, and then integral of the second function, so e to the power minus of st by minus of s d of t. So this will become at t is equals to infinity, this is going to 0, and at t is equals to 0 this is 0. So this is 0 plus 1 by s integral from 0 to infinity e to the power minus of st d of t. So when we have integrated again, then it will become e to the power minus of st by minus of s, then integral from 0 to infinity. So again at t is equals to infinity this is going to 0, at t equals to 0 this will become 1. So this is 1 by s square. Similarly we can find out Laplace transform of t square. So if we find out the Laplace transform of t square, it will be integral from 0 to infinity e to the power minus of st t square dt. Then you again do the integration by parts, very basic, and you will find out it will become 2 by s cube, where s is positive, of course s is positive. So as we can see Laplace transform, we know that Laplace transform of 1 is 1 by s, Laplace transform of t is 1 by s square, Laplace transform of t square is 2 by s cube. If you do Laplace transform of t cube, then you will find, I mean because doing the integration by parts for t cube is rather easy, we will find it is 3 by 2 into 3, that means 6 by s to the power 4, where s is positive. So if you keep on doing by induction, we can write Laplace transform of t to the power n is factorial n by s to the power n plus 1, where s is positive. So this is the general formula. So that means if you put t is equal n equals to 3, it will be factorial 3, that is 6, and divided by s to the power 4. And you keep on doing it. So where n is any positive integer, of course n has to be a positive integer, otherwise we may not get it, right. So positive integer union 0 also, so that is, for that also it is valid. Okay, now let us go to the next page, next function. Suppose if our given function is Laplace transform, our ft is e to the power alpha t, where alpha is any positive number. So then in that case we will have Laplace transform of e to the power alpha t. So this will become integral from 0 to infinity e to the power minus of st e to the power alpha t dt. So this will become integral from 0 to infinity e to the power alpha minus s t dt. So if I integrate by parts, then in that case it will become e to the power alpha minus s by alpha minus s, of course t, 0 to infinity. So if if s is greater than alpha, if s is greater than alpha, then this will become negatives, and then in that case only E will go to 0. Otherwise, if alpha is greater than S, then it will go to infinity. So we have to have when S is greater than alpha, so definitely we need to have S is greater than alpha. It will become 1 by alpha minus S, or minus of S minus alpha, right, and with a negative sign here, so this will become plus. Yeah, so here S must be greater than alpha. So for exponential function, we will get this as a Laplace transform. So when alpha is 1, basically we will have Laplace transform of e to the power t as 1 by S minus 1. Okay, now fourth number will be Laplace transform of cos of alpha t. So this will become integral from 0 to infinity cos of alpha t e to the power minus of st dt. Here you have to do that integration by parts, where you have one function as cos, another function as exponential. You must have done it before, and if you do this calculation, you'll end up getting s by s square plus alpha square, where s is positive. And similarly, if you have a Laplace transform of sine of alpha t, then you again do the integration by parts. That means 0 to infinity sine of alpha t e to the power minus of st dt, and if you do the integration by parts, you will be able to obtain alpha by s square plus alpha, where s is positive. So for these classical functions, if you know the Laplace transform, I mean, you have to memorize them, because they are very classic. I mean, you cannot afford to calculate during your examination. So you have to memorize these Laplace transform, and if you know them, then writing their inverse Laplace transform is very easy. So that means when you are writing the inverse Laplace transform, L inverse of, let's say, 1 by S, so you can directly write 1, because Laplace transform of 1 is 1 by S. So when you charge the inverse operator on both sides, this side it will become 1, other side become L inverse of 1 by S. Then we have L inverse of 1 by s to the power n plus 1. So this will become t to the power n by factorial n, because Laplace transform of t to the power n is factorial n by s plus 1, s to the power n plus 1. Similarly, inverse Laplace transform of 1 by s minus alpha will be e to the power alpha t, provided s is greater than alpha. And fourth one is inverse Laplace transform of 1 by s square plus a square. So this will be 1 by a sine of at. Then we have fifth L inverse of s by s square plus a square. So then this will be cos of at. Then sixth one is L inverse of 1 by s square minus a square. Then this will be 1 by a sine of hyperbolic at, because Laplace transform of sine of hyperbolic at will be a by s square minus a square. Seventh number is Laplace transform of inverse Laplace transform of s by s square minus a square. So this will be cos of hyperbolic at, right? So these are some of the classical inverse Laplace transform. So we have Laplace transform, then we have inverse Laplace transform. Okay, now we'll come to the definition part. That can we say that all the time Laplace transform will exist, or is there any possibility that for some functions Laplace transform will not exist, right? So before we do that, I'll give two definitions. So definition 1, a function ft, a function f is said to be piecewise, or some people also call it sectionally, section-wise, continuous on a closed interval a less than or equal to t less than or equal to b, if it is defined on that interval, and be such that the interval can be subdivided into the finite number of intervals in which in each of which ft is continuous. Right. So, piecewise continuous. As the term says piecewise, that means you have the entire interval. It is not continuous on the entire interval, otherwise it will be uniformly continuous. So, when we say that piecewise, that means suppose you have AB, then you know the partition, right? So, you take n partitions, or I don't know, it can be 3 partitions, 4 partitions. Let's say you have taken n partitions. So, in each one of these subintervals, small subintervals, the function is continuous. So, hence you can call it as piecewise continuous function, right? You divide the interval into small subintervals. If it is continuous in all of them, in each of them, then it is piecewise continuous. And a function ft is said to be of exponential order as t tends to infinity if there exists a constant, a positive, such that e to the power minus of at into mod of ft is bounded. We don't have to put mod on e because exponential is always positive, is bounded for all t greater than capital T. That is, there exists a constant capital M such that we have mod of ft is less than capital M e to the power at. And in that case, the function f is called function of class A, function of class A, right? So, this is what we mean by function of exponential order. So, now if you have a function of exponential order, how we connect the existence of a Laplace transform, that is what we are going to state next. So, now our next article is existence of Laplace transform. Existence of Laplace transform. So, this is a theorem, basically a theorem. Let f be a piecewise continuous function on an interval a comma b for, or 0 comma capital T for every positive t, and let f be of exponential order as t tends to infinity for some a. Then the Laplace transform of f exists for s greater than a, right? So, then it exists for s greater than a. So, this is basically the existence theorem for Laplace transform. That means the function f that is given to us has to be piecewise continuous and it has to be of exponential order. Then only that Laplace transform, the improper integral, remember it is an improper integral. So, we have to make sure that it converges. It is not like it is infinite. So, since you have an improper integral, we have to make sure that integral exists or not. And in order to make sure that it exists or not, these two property has to be satisfied, right? So, because of that, I mean, we can look into the proof. So, the proof is very small. So, since f is piecewise continuous and it's of exponential order. If I take the Laplace transform of f, remember it will be in mod of, if I take mod of, so then mod of integral from 0 to infinity e to the power minus of st ft dt. So this will be less than or equal to integral from 0 to infinity e to the power minus of st mod of ft dt. But ft is of exponential order, that means we can write it as capital M e to the power at. It should be less or equal to capital M 0 to infinity capital M e to the power minus of st e to the power at dt, because f is of exponential order, right. So we have already defined this. So this will be capital M integral from 0 to infinity e to the power minus of s minus a t dt. So when we integrate, this will become capital M e to the power minus of s minus a t by minus of s minus a 0 to infinity. Now from here, if s is greater than a, then only this exponential will go to 0. Otherwise, if s is less than a, then in that case e to the power positive will come, and when t tends to infinity, that will blow towards plus infinity. So that we do not want. So this will converge to capital M by s minus a only when s is greater than a, and therefore thus integral from 0 to infinity e to the power minus of st ft dt is less than or equal to capital M by s minus a when s is greater than a. That means this will be bounded by, so capital M is a positive number, s is a positive parameter, or in this case it could be a number, and a is a number. So ultimately the right hand side is finite, none of them is going towards infinity. So this basically integral from 0 to infinity, of course its mod is bounded by a positive quantity, that means the function itself will be bounded. And this tells us that this integral will exist. I mean, if this right hand side had gone towards infinity, then we could not say whether the left hand side will exist or not. But since this quantity is less than infinity, that means the integral itself must exist. So this must exist. So that means if the function is of exponential order and piecewise continuous, then it is of class A, and if it is of class A, then Laplace transform exists. So indirectly we can say that if the function is of class A, then only Laplace transform will exist. So we can put a nice small summary that if ft is of class A, then only Laplace transform of f exists. Simple. Class A means it has to be piecewise continuous and it has to be of exponential order. So if it is of class A, then its Laplace transform will exist. So all the classical functions that we have taken, they are all not only piecewise continuous, they are continuous on the entire interval, and of course they are of exponential order. So therefore their Laplace transform always existed, right? But in general, you can always verify whether the function is of class A or not, then we can only say that it has a Laplace transform. Now, since we have Laplace transform and it is an operator, right? Capital L is an operator. So an operator has several properties, whether it is linear, whether it is distributive, associative, and things like that, continuous. So here we will summarize some properties of Laplace transform. So the first one is linearity, or sorry, properties of Laplace transform. So the first one is linear property. So what is linear property? Laplace transform of C1 f1t plus C2 f2t is equals to C1 Laplace transform of f1t plus C2 Laplace transform of f2t, only one bracket, f2t. So that means here basically our Laplace transform will get distributed on both the f1 and f2. Proof is very simple, because here when you write integral from 0 to infinity e to the power minus of st c1 f1t plus c2 f2t d of t. So this can be written as c1 integral from 0 to infinity e to the power minus of st f1 dt plus c2 integral from 0 to infinity e to the power minus of st f2 dt. Now this is the Laplace transform of f2, this is the Laplace transform of f1. So this is c1 L of f1 and this C2 L of F2, right? So of course Laplace transform is linear. Then we have another property that is called shifting property. So this is very important and we will use it every now and then. So first shifting property, So if the Laplace transform of Ft be Fs, then the Laplace transform of e to the power at f of t is f of s minus a. That means you can shift the origin in a way. So you can go from s to s minus a, right? So Laplace transform e to the power at ft will be f of s minus a. Of course, there is a proof involved, but proceeding in the similar fashion from the definition, you will be able to derive this, right? So it's not so complicated. Third property is change of scale. Property. So change of scale says that if Laplace transform of Ft is equals to f of s, then Laplace transform of f of at will be 1 by a f of s by a. This helps when you have some constant times, let's say sine t, sine of 5t. So then that is an example of Laplace transform of Ft equals to this. So what is the Laplace transform of f of at? That means f of sine of 3t. So then you can use this formula and you can determine, right? So this is change of scale property. Then we have something called second shifting property, and we also have convolution. So I should state the Laplace transform of the integrals. So this is Laplace transform of integrals, the last property. Then we'll continue Laplace transform. Then rest we will continue in the next class. Laplace transform of integrals. So in the next class, I will also state what is the Laplace transform of derivative. So Laplace transform of integral will be, so L of f of t is equals to f of s. So then Laplace transform of integral from 0 to t f of tau d tau is equals to f of s by s, or 1 by s Laplace transform of f of t, right? So for integrals it is this. Similarly, there is a Laplace transform for derivative. In fact, derivative of n order, right, of nth order. That means dn by dxn, something like that. So dn by dtn. So there is a nice formula for that. I will write down the formula, and if time permits, then also show the derivation of the derivative. Then we'll talk about convolution and maybe one or two more derivations related to the property of Laplace transform, and then we'll actually go to the solution of ordinary differential equation. So I'll stop here today and we'll continue this discussion on Laplace transform in our next class.